Exercise questions of chapter moving charges and magnetism. Question 1: a circular coil of wire 100 turns, each of radius 8 centimeter, carries a current 0.4 ampere. What is the magnitude of the magnetic field B at the center of the coil? Okay. So equation for magnetic field at the center of the coil, circular coil, B is equal to mu naught by 4 pi, mu naught by 4 pi, 2 pi I, 2 pi I by R into N. We have to multiply by number of turns. Now, all those quantities are given in the question. You can substitute the values. Mu naught by 4 pi is 10 power minus 7. So when you substitute the values, you will get the answer. Then next question 2. A long straight wire carries a current of 35 ampere. What is the magnitude of the magnetic field B at a point 20 centimeter from the wire? Again, magnetic field produced by straight wire. The formula is B is equal to mu naught by 4 pi, mu naught by 4 pi 2I by R. Value of current and distance R, all these quantities are given. Substitute the values and find the answer. Question number 3. A long straight wire in the horizontal plane carries a current 50 ampere in north-south direction. The current is in north-south direction. So like this, we can draw the direction north-south direction. Current I goes. Give the magnitude and direction of magnetic field at a point 2.5 meter east of the wire. So we have east-west direction. Now 2.5 meter east. So the field point P we can take here. And what is the direction of the magnetic field? Again, formula for magnetic field due to a straight conductor B is equal to mu naught by 4 pi 2I by R. Substitute the values, you get the value of B. Now apply right hand thumb rule. When you apply right hand thumb rule, you can see the direction of magnetic field at the point P is upward. Then next, question number 4. The horizontal overhead power line carries current 90 ampere in east to west direction. So here the current is in east to west direction. East to west, it carries current I. Now, what is the magnitude and direction of the magnetic field due to the current 1.5 meter below the line? 1.5 meter below the line. Here you can see we can take the north-south direction like this. Suppose it is south, this is north, and 1.5 meter below. Again, you can see formula will be same only. B is equal to mu naught by 4 pi 2I by R. Then right hand thumb rule you can apply. So if you take the axis like this, then you will get the answer here. Magnetic field will come like this at this point. So the magnetic field is towards south. Towards south. You get the magnetic field, provided you have to consider the axis in a east to west, north south, in a horizontal plane. You have to consider, and only you get the answer in that way. Okay, now question 5. What is the magnitude of magnetic force per unit length on a wire carrying current of 8 ampere and making an angle of 30 degree with a direction of uniform magnetic field of 0.15 Tesla? Okay, so force acting on a current carrying conductor in magnetic field F is equal to I L B sine theta. I B sine theta. Here you have to take L is equal to 1 meter because force per unit length is asked there. So L is equal to 1 meter. Then substitute the values in the formula and find the answer. Then question 6. A 3 centimeter wire with the current at 10 ampere. Okay, placed inside a solenoid. Inside the solenoid there is a uniform magnetic field perpendicular to its axis. That means angle between current and magnetic field is 90 degree. Okay. Then the magnetic field, value of magnetic field is given. What is the force? So again, formula will be same. Force on a current carrying conductor in magnetic field F is equal to I L P sine theta. The value of theta is 90 degree here. So substituting the values, you will get the answer. Then next question 7. Two long parallel straight wires A and B carrying currents of 8 ampere and 5 ampere in the same direction are separated by a distance of 4 centimeter. Estimate the force on a 10 centimeter section of wire A. So force between parallel current you have to take. Force F is equal to mu naught by 4 pi 2 I1 I2 upon R into L. All the quantities you have to substitute in SI unit, then you will get the answer. Then next question 8. A closely wound solenoid 80 centimeter long has 5 layers of windings 400 turns each. So total 400 into 5, that is 2000 turns are there. The diameter of the solenoid is 1.8 centimeter and the current 8 ampere. Estimate the magnitude of magnetic field inside the solenoid. The formula is P is equal to mu naught Ni, where N is the number of turns per unit length, which can be found as mu naught into total number of turns upon length into I. So substitute the values and find the answer. Question number 9. A square coil of side 10 centimeter consists of 20 turns and carries a current of 12 ampere. The coil is suspended vertically and the normal to the plane of the coil makes an angle of 30 degree with the direction of a uniform horizontal magnetic field of magnitude of 0.8 Tesla. What is the magnitude of torque? And torque formula, torque is equal to mb sine theta, and magnetic moment m is equal to nia. So you will get NIAB sine theta, and all the quantities are there. Substitute and find the answer. Question number 10. Two moving coil galvanometers, okay, M1 and M2, with the resistance, area, magnetic field. All these factors are given in the question. Now, we are asked to determine first the ratio of current sensitivity and second voltage sensitivity. So current sensitivity formula, we have the first one. I am going to take IS1. IS1 is equal to N1 B1 A1 upon K. And because it is given the spring constants are identical for the 2 meters. So we have the same value of K. Now IS2 is equal to N2 B2 A2 upon K. Now you have to take the ratio IS2 upon IS1. IS2 upon IS1, you get N2 B2 A2 upon N1 B1 A1. So substitute the values, you get the answer of the ratio for current sensitivity. Next we have voltage sensitivity for part B. For voltage sensitivity, first we can take voltage sensitivity of the first galvanometer VS1. VS1 is equal to IS1 upon R1, and VS2 is equal to IS2 upon R2. Now take the ratio VS2 upon VS1 is equal to IS2 upon IS1 into R1 upon R2. The ratio of IS2 to IS1 has been obtained from part A. So substitute these values, you will get the ratio of voltage sensitivities. Next, question 11. In a chamber, a uniform magnetic field of 6.5 Gauss conversion formula is given. 1 Gauss is equal to 10 power minus 4 Tesla is maintained. An electron is shot into the field with a speed of 4.8 into 10 power 6 meter per second normal to the field. Explain why the path of the electron is circled. So we have to explain, okay, the magnetic force does no work. So the path is circular, okay, which you have studied in theory. Now determine the radius of the circular path. Okay, you have the data. You need to just substitute the values. R is equal to mv upon bq. So substitute and find the answer. Then question 12. It's a continuation of the previous question. Obtain the frequency. Okay, all quantities are given. So frequency nu is equal to VQ upon 2 pi m. That is the equation for frequency. Substitute the values, obtain the answer. Charge is electronic charge, mass is mass of the electron. Now question 13. A circular coil of 30 turns and radius 8 cm carrying a current of 6 ampere is suspended vertically in a uniform horizontal magnetic field of magnitude 1 Tesla. The field lines make an angle of 60 degree with the normal of the coil. Calculate the magnitude of the counter torque that must be applied to prevent the coil from turning. That means you have to find torque, that's only. And torque formula, again, tau is equal to mb sine theta, and value of m is nia b sine theta. So substitute the values and find the answer. Part B, would your answer change if the circular coil in part A were replaced by a planar coil of some irregular shape and encloses the same area? All other particulars are also unaltered. So you can see torque is independent of shape. It depends on area only. So far the area remains same, no change in the value of torque, you will get the same value of torque in this case also. Okay. Now, question 14. Two concentric circular coils X and Y of radius 16 centimeter and 10 centimeter respectively lie in a same vertical plane containing the north to south direction. The coil X has 20 turns and carries a current of 16 ampere. Coil Y has 25 turns and carries a current of 18 ampere. The sense of the current in X is anti-clockwise and clockwise in Y. For an observer looking at the coils facing west, give the magnitude and direction of the net magnetic field due to the coils in their center. So first of all, we have to make a diagram based on the question. So we have two coils X and Y. Now these two coils, okay, are in the same plane. So we can have coil X and coil Y. Okay. Now in coil X, current is in clockwise direction. So current, we can say Ix in clockwise direction, while in coil Y, it is Iy in anti-clockwise direction. Now we can, let's see there, the observer. Okay, so here we can take the axis of the coil like this. Now here west and east, and the observer is standing here, and the observer is facing towards west. When he is facing towards west, we can see here. First, take the case of coil Y. He is observing. Is observing the current in the coil in By in anti-clockwise direction, which means he is facing north pole. So magnetic field due to By magnetic field due to By coil X. Okay, the sense of the current in X is anti-clockwise. Just here, the current in X is anti-clockwise. Current in X is anti-clockwise Ix, while Iy in clockwise. Current in Y is clockwise. Okay, now current in Y is clockwise, which means for Y, okay, is facing south pole for Y. For Y, it is south pole, and towards here, it is north pole, and magnetic field is from south to north, so By is towards west. Now for coil X, he is observing anti-clockwise direction. Therefore, for coil X, this side, the side which he is facing is north pole, and other side is south pole, and the magnetic field is from north to magnetic field is from south to north inside. So here the value, the direction of X is towards the observer, Bx. Now that means Bx is towards east, By is towards west. Now the coil Y has stronger current, more number of turns, and less radius. Therefore, Y produces a stronger magnetic field. That is, we can have net magnetic field B is equal to By minus Bx. By is stronger than Bx. We can substitute the equation for magnetic field at the center of a circular coil. So we have mu naught by 4 pi, mu naught by 4 pi, 2 pi I by n by, you have to multiply by number of turns also, upon r y, the radius, minus mu naught by 4 pi, 2 pi ix nx upon rx. Common factors we can take outside so that you will get a net magnetic field B is equal to mu naught by 4 pi 2 pi into Iy ny over ry minus ix nx upon rx. Substitute the values in SI unit, you get the value of net magnetic field, and this magnetic field is towards the net magnetic field is towards west. Now, question 15. The magnetic field 100 gauss is required, which is uniform in a region of linear dimensions about 10 centimeter and area of cross section about 10 power minus 3 meter square. The maximum current carrying capacity of the given coil of wire is 15 ampere. I max is given 15 ampere. And the number of turns per unit length that can be wound round a core is at most 1000 turns per meter. Means maximum number of values, number of turns per unit length is 1000. Suggest some appropriate design particulars of a solenoid. Okay, solenoid, we have formula solenoid B is equal to mu naught Ni. Now find the value of Ni. Ni is equal to B upon mu naught. Substitute the values of B and Ni, you will get the answer approximately 8000. Approximately 8000 ampere per meter. Now, this 8000, we can see maximum number of turns 1000, maximum current 15. Let I is equal to 10 ampere. We need to take less than 15. That's only. I is equal to 10 ampere. Then N will be 800, which is less than 1000 number of turns per unit length. So you can construct a solenoid with those specialities. Now, question 16. For a particular coil of radius r and n turns carrying current I, the magnitude of the magnetic field at a point on its axis at a distance x from its center is given by, okay, this is a formula magnetic field at the axis of a circular coil V is equal to mu naught by 4 pi, then mu naught by 4 pi into 2 pi I r square n upon r square plus x square the whole raised to 3 by 2. Okay, show that this reduces to a familiar result for field at the center of the coil. At the center of the coil, value of x is equal to 0. At the center, x is equal to 0. When x is equal to 0, you will get the value of B center. B at the center is equal to mu naught by 4 pi 2 pi I upon R. This is the equation. Now, part B, the solution is given in the last pages of the textbook. Please go through that. Okay. Then, this type of an arrangement, okay, of two circular coils, nearly, okay, such coils, that arrangement of such coils, we call the name Helmholtz coil. Please remember the term. Okay. So usually the such coaxial coils are used to get uniform magnetic field. In between those two coils, there will be a small region of uniform magnetic field. And that's the purpose of using such a coaxial coils known as Helmholtz coils. Then, question 17. A toroid has a core of inner radius 25 centimeter and outer radius 26 centimeter, around which 3,500 turns of a wire are wound. If the current in the wire is 11 ampere, what is the magnetic field? First, A, outside the coil. We know outside magnetic field is 0 for a toroid. Then, inside the core of the coil, B is equal to, the formula is mu naught, magnetic field B is equal to mu naught Ni, that is equal to mu naught into, again small n is given, so capital N upon 2 pi r, because it is circular, the length is 2 pi r into I. Then you can substitute the values, you will get the answer. Now value of r you have to take as r is equal to the average radius, outer radius plus inner radius over 2. You will get the value of r. And finally, part C, in the empty space surrounded by the solenoid, again you can see in the empty space there is no magnetic field, so it is 0. Then next, question 8. Sorry, question 18. A magnetic field that varies in magnitude from point to point but has a constant direction east to west is set up in a chamber. A charged particle enters the chamber and travels undeflected along a straight line with a constant speed. What can you say about the initial velocity of the particle? So there are two possibilities, that a moving charge does not experience force in magnetic field. The first possibility, that velocity of the particle should be parallel to the magnetic field. And second possibility, it should be anti-parallel to the magnetic field. We have the formula F is equal to Q into V cross B. V cross B, when you take cross product, it is VB sin theta. So when theta is equal to 0 degree, or theta is equal to 180 degree, sine value you will get 0, so that force becomes 0, the particle goes straight. Part B, a charged particle enters an environment of a strong and non-uniform magnetic field varying from point to point, both in magnitude and direction, and comes out of it following a complicated trajectory. Would its final speed equal the initial speed if it suffered no collision with the environment? Okay, so we know magnetic force does no work. It cannot change the kinetic energy of a particle. Therefore, it will come out with the same velocity. Then, part C. An electron traveling west to east enters a chamber having a uniform electrostatic field in north to south direction. Okay, let's draw the diagram. So we can have north, south, east, west directions. Then the electron is traveling from west to east. Electron is traveling from west to east, while current is from east to west. Specify Specify the direction of the uniform magnetic field. Should be set up to prevent the electron from deflecting from its straight line. Okay. So here, uniform electric field is from north to south. Direction of electric field. So direction of electric field is from north to south. Electric field. So electron experiences a force opposite to the direction of electric field. So as electron experiences force opposite to the direction of electric field, then Fe, force on electron due to electric field, is towards north. Now, we want to keep the electron moving without deflection, which means an equal amount of force must be applied by the magnetic field. Equal amount of force must be applied by the magnetic field in the opposite direction. So, force due to magnetic field should be towards south. Now, you can see there, current is from east to west. Force due to magnetic field is from north to south. Use Fleming's left hand rule. Then you can see the magnetic field should be vertically downward. Magnetic field is vertically downward. Then only it should be equal and opposite to electric field. So in such a situation, when Fm equal to Fe, when with a magnetic field acting vertically downwards, the electron goes undeflected. Next question 19. An electron emitted by a heated cathode and accelerated through a potential difference of 2 kilovolt enters a region with a uniform magnetic field of 0.15 Tesla. Determine the trajectory of electron if the field case A is transfers case A is transfers to its initial velocity. B makes an angle of 30 degree with the initial velocity. So here, in the first case, okay, so we need to explain why the trajectory of electron. We know when it is normal, then it is 90 degree. 90 degree means the electron follows circular path. Okay, so all these you have seen in theory, we need to give the same explanation. Now, when 2 kilovolt potential is applied, you can take work done is equal to QV is equal to EV is equal to EV, and this work is converted into kinetic energy half m v square. Kinetic energy half m v square. From that formula, you can find the value of velocity. V is equal to under root 2 EV upon m. You will get the velocity of electron. And in case A, we have seen the particle follows circular path, so that R is equal to mv by bq. You will get the equation for you will get the answer for radius of the circular path. And in case B, it makes an angle of 30 degree with the initial velocity. So as it makes an angle other than 90 degree, it follows helical path. When it is in helical path, again the radius of the helix will be mv sin theta. Theta is equal to 30 degree. It is given mv sin theta by b2, and you can find the pitch of the particle also. Okay, it is not specifically mentioned there. Still, you can find the pitch also. Then, question 20. A magnetic field is set up. Okay, again, Chemcore's coils, arrangement of two coils. Okay, magnetic uniform magnetic field. We have 0.75 Tesla. Accelerating voltage is 15 kilovolt is given there. Then the beam remains undeflected, the same velocity selector condition. Okay, electric field is 9 into 10 power minus 5 volt per meter. Then make a simple guess to what the beam contains. So usually, okay, what particles in the beam? That is what we need to find out. There, you can see. Usually, we identify the particle with its E by M, charge to mass ratio. So here also we take the same concept. We have kinetic energy of the particle half m square is equal to v square is equal to EV, where E is the charge of the particle, EV. Now from there you can find the value of E by M. E by M is equal to V square upon 2V. E by M is equal to V square upon 2V. Then again for velocity selector, the particle goes undeflected when velocity V is equal to the ratio of electric field to magnetic field. So value of V you can substitute in the equation, then you will get E by M, charge to mass ratio, E by M is equal to E square upon 2b square V. E square upon 2b square V. So you can substitute the values and you will get the answer approximately. You will get a 4.8 into 10 power 4.8 into 10 power 7 coulomb per kilogram. Coulomb per kilogram. And such an E by M value usually for neutron, the second hydrogen with a neutron. Okay, and but the value is not unique, so the possibility is there for helium 2 plus or for lithium 2 plus, and so uh, these ions are also having almost same E by M. Therefore, the answer is not unique. Now, question 21. Okay, a straight horizontal conducting rod of length 0.5 meter and mass 60 gram is suspended by two vertical wires at its ends. A current of 5 ampere is set up in the rod through the wires. What magnetic field should be set up normal to the conductor in order that the tension in the wires zero? So here we have a fixed point, then two wires, and these two wires you can see here a conductor is hanging. Now the weight mg is acting downwards and tension in the wire are acting upwards. Now tension zero means you have to set up a magnetic field in such a way that the magnetic field gives a force upwards, and that force due to magnetic field is equal to mg. At that situation, mg got cancelled, so that no tension on the wire. So force due to magnetic field, okay, force experienced by magnetic field is ILB. ILB is equal to mg. ILB is equal to mg. So from there, you can find the magnetic field B is equal to mg upon IL. So substitute the values, you get the value of the magnetic field to be set up so that the tension on the suspension wires is zero. Now case B, what will be the total tension in the wires if the direction of the current is reversed, keeping the magnetic field same as before? When direction of current in the conductor reverse here, current direction reverse, which means force due to magnetic field now in the opposite direction, which is downward. Therefore, the total force will be F total is equal to force due to magnetic field plus mg. Now both are acting downward is equal to, already we have seen with this magnitude, if all other quantities remains constant, mg is equal to ILP. Therefore, Fm is equal to mg plus mg. So that is equal to 2 mg acting downward, so that you can find the value. Now, question 22. The wires which connect the battery of an automobile to its starting motor carry a current of 300 ampere. What is the force per unit length between the wires if they are 70 centimeter long and 1.5 centimeters apart? Is the force attractive or repulsive? So here we can have the battery. Okay, so positive terminal and negative terminal, positive terminal and negative terminal, and from there the wire is running parallel. The wire is running parallel, okay, to whatever device it is. Now the current goes from positive terminal and returns back to negative terminal. That is our concept. In this situation, you are asked to calculate what is the force per unit length. So, parallel current force we have to take. F is equal to mu naught by 4 pi. F is equal to mu naught by 4 pi 2 I1 I2. Here, both I1 and I2, you have I only, 2 I1 I2 L upon R. R is 1.5 centimeter and L you have to take 1 meter because force per unit length is asked. So substitute the values, you get the answer. Now here the currents are anti-parallel currents. So as they are anti-parallel currents, they will repel each other. Now next, question 23. A uniform magnetic field 1.5 Tesla exists in a cylindrical region of radius 10 centimeter. Its direction parallel to the axis along east to west. A wire carrying current 7 ampere in the north to south direction passes through this region. What is the magnitude and direction of the force on the wire if three cases are given there? So first of all, let's see a diagram. Cylindrical region having magnetic field is in the east to west direction. So just you draw like this, the east to west direction. East to west direction. Now here a cylindrical region. Okay, the magnetic field we can take like this, a cylindrical region in this way. So here the cylinder, only in this region the magnetic field is present. Then a wire carrying current, okay, is vertically like this, and current direction is given. Current direction is from north to south. We have north, south, current direction. Now current and magnetic field are perpendicular. Okay, so first case the wire intersects the axis, just like this diagram. So we can have in case A, you have force F is equal to I L B. Okay, because current and magnetic field are perpendicular. So substitute the values, find the answer, and apply Fleming's left hand rule. You will get the you will get the direction of force as downward. And here, what is the length of the wire? The length of the wire you have to take as the diameter of the cylinder, because magnetic field is present only in this area, not outside. Magnetic field is present only in that area. As magnetic field is present only inside, length of the wire you have to take as the diameter. And the next one, so what happens there? The wire is turned from north south to northeast northwest direction. Northeast northwest direction. So here again you can see the magnetic field, cylindrical region. Like this, the cylinder we can imagine. That cylindrical region, magnetic field is present. So west, east direction. Now here, north south direction. Then the wire is turned something like this. The wire is turned just something like that. It is lifted in this way. It will come. Okay. So here, as it is shown, there is no cross section at all. This magnetic field is present throughout. I mean, the magnetic field is extending in the cylindrical pattern towards here like this. Okay, in such a situation, for convenience, we can draw a parallel line here, and assuming the magnetic field is sorry, the wire is here. Okay, in this way, it will pass us through the cylinder and the current. Now you can see here, this current we just assume, okay, length of the conductor, IL together a vector, So IL vector we can resolve into perpendicular components like this. Perpendicular components. Now, two components are there. In the first part, you can see the here the current is parallel to magnetic field. If current is parallel to magnetic field, it cannot apply any force there, because IL cross B, our formula is IL cross B, F is equal to IL cross B, then is equal to ILB sine theta. So what happens? This parallel component, here current and magnetic field are parallel, theta is equal to 0. As theta is equal to 0, this component cannot have any force, F is equal to 0. And the vertical component, when you see vertical component is same as in the first case, okay, vertically. So you can use the formula F is equal to ILB, F is equal to ILB. So you will get the answer. L is again diameter, and in the same direction downwards it will be acting. Okay. Now case C, the wire in north-south direction is lowered from the axis by a distance of 6 centimeter. For case C, the wire is lowered. So let us see here, only the cylindrical part I am going to draw the cross section. Now In that cross section, the wire, just assume that initially the wire is like this through the diameter. The current is going in this way. Now the wire is lowered for 6 centimeter here. This distance is 6 centimeter. So that now the wire is here. So you have to calculate only how much length of the wire is inside. That is what you need to find it in the magnetic field. This much wire only inside. So how can you find the length here? You can construct right angle triangle. This is radius 10 centimeter. This is also radius 10 centimeter. So from the right angle triangle, you can calculate uh, 6 centimeter, 10 centimeter. So what is the length? The length will be, um, we have to find the total length. Total length will be 2L is equal to 2 into under root 10 square 10 square minus 6 square is equal to 2 into 8 is equal to 16 centimeter. Now for finding force, use the formula again, ILB. L is equal to 16 centimeter. Substitute the values, find the answer. Then question 25. A circular coil of 20 turns and radius 10 centimeter is placed in a uniform magnetic field of 0.1 Tesla normal to the plane of the coil. If the current in the coil is 5 ampere, what is the total torque? Torque formula is torque is equal to NIAB sin theta or MB sin theta. Now what is theta there? If it is NIAB sin theta, NIAB sin theta. Theta is the angle between area of the coil and magnetic field. Here it says magnetic field is normal to the plane of the coil. If magnetic field is normal to the plane of the coil means you can find the area of the coil by drawing a normal. Now magnetic field is also normal. Magnetic field is normal means here you will get a angle theta is equal to 0. As theta is equal to 0, sine 0, 0, so not torque, you will get the answer 0. Now total force, okay, the force also will be 0. The torque is acting, so force will be 0. Then what is the average force on each electron in the coil due to magnetic field? So average force on each electron in magnetic field. So force on electron, we can have magnetic force E into VD cross B. Okay, VD E into VD cross B. You will get the magnetic field. Now, value of VD you can find out. VD is equal to I upon NEA because I is equal to NEA VD formula you have studied. Okay, from that equation, substitute the value of VD there, then you will get a force F is equal to BL divided by N into A. BL divided by N. Here when you VD, when you substitute, BI divided by, okay, sorry. BI divided by NA will give the answer. This again, N is small n, will give you the final answer. And those quantities, okay, number of free electron density N is given here, 10 power 29. Cross-sectional area is also mentioned here. Those values you have to substitute here to get the answer. Now, number 26, question number 26, a solenoid uh, 60 centimeter long and of radius 4 centimeter has three layers of windings of 300 turns each. So total we have 900 turns. A 2 centimeter long wire of mass 2.5 gram lies inside the solenoid normal to the axis. Both the wire and the axis of the solenoid are in the same horizontal plane. Okay. The wire is connected through two leads parallel to the axis of the solenoid to an external battery which supplies a current 6 ampere. 6 ampere is the current passing through the wire. So now, what is the value of the current in the windings of the solenoid? Current through solenoid you have to find to support the weight of the wire. So now the magnetic force F is equal to ILB. F is equal to ILB, where I is the current through the wire, length L is the length of the wire, is equal to mg, then it will be uh, suspended there. Now, what is the value of B? Solenoid magnetic field B is equal to mu naught N. Instead of small n, capital N by L, that is length of the solenoid you have to take mu naught N by Ls into I. I is the current through the solenoid. Now substitute this value here, value of B in the formula. You will get IW LW mu naught N upon Ls into Is is equal to mg. Now cross multiply the equation for Is, substitute all values in SI unit, you get the answer. Question 27. A galvanometer coil has a resistance 12 ohm and the meter shows full scale deflection 3 meter, that is IG, 3 milliampere. How will you convert the meter into a voltmeter of range 0 to 18 volts? So you need to connect a high resistance in series, and the equation for that high resistance R is equal to V by I. V is 80. V by Ig. Ig is the current for full scale reflection minus Rg. Rg is the galvanometer resistance. By connecting resistance R, you can construct galvanometer. Now, question 28, a galvanometer coil has a resistance of 15 ohm and meter shows a full scale deflection for a current of 4 milliampere. How will you convert the meter into an ammeter of range 0 to 6 meter? You have to connect a shunt resistor parallel to galvanometer, and the value of shunt resistor is given by IGRG upon I minus Ig. IGRG upon I minus Ig will give you the value of shunt resistance, or the quantities are given in the question.